Hello everyone, welcome back to the Quantum Mic and another Quantum Mic classic. As you may know by now, the Quantum Mic was originally a podcast prior to being a YouTube series. And I did this back during the COVID-19 pandemic. When I hosted the Quantum Mic podcast, I interviewed physicists and people involved in physics about their research and their experiences in the physics community. Today, I want to make one of those interviews available to you. So make sure to plug in your earbuds and let's listen to my interview with Dr. Daniel Stolarski, where I talk to him about emerging jets and the Higgs Boson. It's very interesting research, so please enjoy. Hello everyone, welcome back to the Quantum Mic. As always, I'm your host Owen, and today we are joined by Dr. Daniel Stolarski, an associate professor at Carleton University. Thank you for joining me today, Daniel.
Yeah, thanks for having me. I'm looking forward to this.
This is going to be a fun interview. Daniel actually taught me E&M in second year of my physics degree program that I'm still in. So this is a great interview to have. Now, would you mind introducing yourself to the listeners a bit more, go in a bit more detail about who you are as a person?
Sure. So I'm Daniel Stolarski. I work at Carleton. So my job as a professor involves teaching physics courses like E&M. This semester, I'm teaching an advanced graduate course in quantum field theory. And I do research in particle physics. So I'm interested in how does the universe behave at the smallest scales, what governs the interactions of everything we see around us and some of the things we don't see around us, and also in the universe at the largest scale. So where did the universe come from? What did it look like in the earliest times before we had stars and planets, and when we just had elements or just had quarks and gluons and electrons and photons. And so I've been doing research on that for some time. Before coming to Carleton here in Canada, I was a research fellow at CERN in Geneva, and I was there when they announced the Nobel Prize for Peter Higgs based on the discovery of the Higgs boson at the Large Hadron Collider at CERN. So that was an extremely exciting time. And I did a lot of interesting research there before coming to Carleton.
That's awesome. So you do particle physics, and if I remember correctly, primarily theoretical particle physics.
Yeah, that's right. So there's two kinds of particle physics research. There's theoretical and experimental. And the experimentalists build the big machines like the Large Hadron Collider that ultimately is the reason we're all doing this research. They're answering the questions of how does nature work. But there's also the theoretical side, and the theory side, we build what are the questions, and then we come up with new ways to answer the question. So I spend most of my time doing what's called phenomenology, which is connecting theory and experiment. So thinking of ways that current experiments could answer new questions, or thinking of new questions that could be answered with future experiments and things like this. And so I don't touch machines. When I was in an undergrad physics program, I had to take lab courses, and I always broke all the machines. So I do theoretical physics, and I don't go inside of labs.
So why theoretical particle physics of all the physics fields to choose from?
Yeah, good question. I mean, it's sort of, I took high school physics and I'm like, oh, physics is cool. And then I took university physics, intro balls rolling down planes, but then it got more advanced and the atom and things like that. And I was like, oh, this is really cool. And then I took an intro to particle physics class, and I was like, wow, this is amazing. We're trying to understand what goes on in the smallest scales, and really what is everything that we know of built out of. And so I was just fascinated by that. And I just went into that in grad school, and I kept going on following that. And sort of more recently, since my time at Carleton, I've been doing a little bit of astroparticle physics, which is sort of the connection between the smallest things and the biggest things, what happened in the history of the universe and cosmology and astronomy. And so I've gotten into that a little bit, but I'm still mostly doing particle physics.
So you primarily do phenomenology. Is there any sort of examples that you could give of the research you've been working on recently in your field?
Sure. So I'm very interested in the Higgs boson. So I think I mentioned that it was discovered in 2012 and the Nobel Prize given for this discovery in 2013. But the Nobel Prize was given to Brout, Higgs, and Engler, who worked on this in the 60s, right? So the theory is actually very old, and they wrote down the very simplest theory of the Higgs boson. And we can talk a little bit more about what is the Higgs and what goes into it. But let me answer your question a little bit more directly first. Is that after it was discovered, you sort of had like these binoculars, and the Higgs you saw was fuzzy. It was clear there was something there, but it was not clear that it was the thing that Peter Higgs and company wrote down in the 60s, right? Was it that thing or was it a different thing? And so a thing I've worked on quite a bit is how can the LHC really carefully test, is the thing that they discovered exactly the thing that Peter Higgs wrote down, or kind of the thing, but also slightly different in a way that maybe is interesting and is related to other mysteries of, what is dark matter or other things we don't understand about the universe, and looking for these very small differences relative to the predictions of the original Higgs model is the kinds of things that I've worked on, and talking about, proposing experiments that or proposing measurements that the experiments can do in order to really test the properties of the Higgs boson.
So following off on that, I guess, for those listeners who don't know, what is the Higgs boson?
Yeah, good. So I guess that's a necessary background, but we'll do this in reverse order, no problem. So in the standard model of particle physics, that's from where we get everything we know. So the periodic table comes from the standard model, and protons and neutrons and electrons. But the standard model without the Higgs boson, it doesn't really make sense. It has this mathematical inconsistency that says basically everything we know has to be massless. It has to move at the speed of light and have no weight. So for example, the electron in the standard model without the Higgs has to travel at the speed of light. But we know electrons don't travel at the speed of light, right? Our bodies are made out of atoms, which have electrons more or less sitting there, not moving at the speed of light. And in fact, if they all did travel at the speed of light, there would be no chemistry. The universe would be a totally, totally different place. And so the Higgs boson fixes this problem. And an analogy that I certainly didn't make up, but is a good one, is that the universe is filled with this Higgs field, which you can think of as like molasses. And so when the electron tries to move at the speed of light, there's this viscous fluid that it tries to move around in that slows it down. And so that keeps it from moving off at the speed of light, and it gives it its weight, and it makes it more likely to be still.
Okay. So you have built a bunch of models for how to test that what the LHC has detected is the Higgs boson particularly.
Yeah, that's right. And there's two aspects of this. The one is building models of like, well, what if it's not the Higgs, what is it? Or if it's kind of like the Higgs, but slightly different, what is the slight difference? But the other aspect that I've worked a lot on is how can you tell the difference? So what measurements can you actually go out and do to tell the difference? And so an example of this is the Higgs. When you make it lives very, very short amount of time. So something like 10 to the minus 24 seconds. So you don't actually, it's not like you take a picture with a camera and you see the Higgs there and you're like, great, I've discovered the Higgs. You see its decay product. So it's produced for a fraction of a second, and then it turns into some other stuff. And so based on the energy of the other stuff, you can tell where the Higgs came from. So for example, one of the things I'm interested in is the Higgs can decay into 2 electrons and 2 positrons. And so if you measure the energy of the electrons and positrons, you can tell it came from a Higgs. But there are other things you can measure. So you can measure, for example, how often are the electrons 30 degrees apart versus 40 degrees apart versus 50 degrees apart. And if you make that measurement very carefully, that can tell you something about, is this really the Higgs that Higgs predicted, or is it something slightly different?
Okay. So what angle has your work on analyzing the angles produced by the Higgs? What is the expected, I guess, angle of these?
Yeah, so there's some distribution of the expected angle, right? It's not the same every time, and right. This is fun quantum mechanics things that, right? Every time the Higgs decays, it looks a little bit different than the last Higgs, and there's some probability, and so you get what a mathematician would call a probability distribution, right? And it's like, but which probability distribution you get is something you can predict using quantum field theory and the modern techniques of particle physics. And you can say, is the angles between 30 and 4 degrees 1.1 times more likely than the angles between 40 and 50 degrees, or 1.3 times more likely? So these are very subtle measurements. The differences are small. You have to collect a whole lot of Higgs bosons to really see any kinds of differences. So we're thinking about collecting 1,000 Higgs bosons that decay exactly in this way to 4 electrons, or to 2 electrons and 2 positrons. And then you can make these kinds of measurements. So some of the stuff I've worked on is a little bit futuristic. It's like, so far the LHC has collected 25 decays to 4 electrons and 4 or 2 electrons and 2 positrons. But if it's intended to run until 2040, and in all the data between now and 2040, it should get enough Higgs boson decays in order to make some of these measurements more precisely.
Okay, I was going to ask, are you using current data, or is it based off future data? Like, because the LHC has been running for years now, and
That's
they're
right.
now
So
being upgraded. So are you looking back at the old data, or are you looking at mainly at the new stuff that's coming up with the higher intensity lasers, or everything in between?
Yeah. So this is a distinction between theorists and experimentalists. I don't look at the data directly. I look at simulated data that I can simulate on my computer or on a big computer cluster, depending on exactly which data. The data is not public, the actual data, and it's, if you talk to an experimentalist, they're like, we couldn't make it public because it's extremely complicated to interpret. But yes, we're proposing that the experimentalists look at data, current data and future data. I would say mostly future data. There is some interesting things you can say with current data, but it gets much, much more interesting with the future data that's upcoming.
So what makes the future data more promising, I guess, or more interesting to look at?
Well, there's more of it is the short answer. As you pointed out, they're upgrading the LHC, which means the LHC smashes protons together. And so they're going to smash a higher frequency of protons together, more and more protons at any given time, which means you will create more and more Higgs bosons. And so you can see more of them and get more details of how the Higgs works. So, I think the expectation is, so far they have 100-ish Higgses, and over this future runs, it'll be closer to 1,000-ish Higgses, right? So you get 10 times more data, so you can make much more precise measurements of any quantity you're interested in. Those numbers I gave are specifically Higgses that decay to 4 electrons, or electrons and positrons. That's a small fraction of the total number of Higgses. That's what's called a rare decay. So only 1 in 10,000 of the Higgses decay in this way, and the rest decay in other ways that are also interesting, but not ways that I haven't worked on quite as much.
Okay, so what are you hoping eventually by 2040, after they have all this data? Are you hoping that your results match what's expected or what was fits the Peter Higgs model, or are you hoping for it to be completely different and throw everything that we know in physics up in the air?
Yeah, fantastic question. No, I'm hoping that the standard model is wrong, and that there's some deviation from the original theory that. Unfortunately, right, we already know that it's approximately right. It's not going to be totally different. So before the LHC turned on, it was possible that really weird, crazy things would happen. But now we know that the original Higgs model is right to within 10% precision at least. But maybe even if it's wrong to 1% precision, if you can really prove that it's wrong, that tells you that there have to be new laws of physics that we don't understand. So that's what I'm hoping for. And I think that's certainly a possibility. But of course, the LHC could have found many discrepancies from the standard model so far. And as of yet, it has found none. The standard model keeps holding up to these very, very impressive tests done by them.
Well, hopefully there's enough new physics out there to keep the physicists all employed for the next few years.
For sure. So I am lucky that I have a stable job and I will be employed, but it's true. I would love all of my students to also get jobs as physicists and continue doing this research. So yeah.
So we were talking earlier, and you said one of the pieces of research that you are most passionate about or proud of was your work on emerging jets. Is that right?
That's correct. So yes, this is some really fun work I did, and it started while I was at CERN. And the idea is that there's this stuff called dark matter, and it makes up most of the matter in the universe, but we can't see it. So you can feel its gravity. It keeps for example, the Milky Way Milky Way would fall apart if dark matter didn't exist. So we know there's something there, but it doesn't appear in any of the elements of the periodic table or in any of the ingredients of the standard model. We know it can't be dark matter. So there's this stuff called dark matter out there. And so of course people have said, well, maybe the LHC can make dark matter. That's a cool idea. There's no guarantee that it could, right? We have no idea what dark matter is, so it could be something crazy, but it could also be related to something you can make at the LHC. And so that's a somewhat old idea. But our idea was that maybe dark matter isn't a single particle. So if you make a single particle at the LHC that's dark matter, it looks invisible. And you can see it by looking for conservation of energy, right? You see a whole bunch of stuff going one way and nothing going the other way. That can't happen. So there's something invisible going the other way. So that's how those are just sort of the traditional searches for dark matter at the LHC. But the assumption there is there's one invisible particle and nothing else. But we know that the standard model is really complicated, right? We know that there's like protons and neutrons and electrons and the whole periodic table, and there's a lot of interesting dynamics. And so maybe whatever is responsible for dark matter is also complicated and interesting. And so when you look for it at the LHC, it looks very different than just a single invisible particle. And so there's these things in the standard model called jets, which is it's very common at the LHC to produce a whole bunch of like protons and other particles going in the same direction, more or less. And so that's called a jet of particles. And this is the most common thing that can happen at the LHC. If you take a gluon and you fire it into the LHC, it turns into a jet. And there's tons of gluons and quarks and all kinds of things. And so what we said is maybe these jets can happen in the dark sector. So the particles that are somehow related to dark matter also make jets. So you get a spray of invisible particles all going in the same direction, but some of these invisible particles are not invisible forever. So they can decay back to standard model stuff. So you start with a whole bunch of invisible particles. So it looks invisible, you see nothing. But then the longer you wait, the more of it becomes visible. So you travel a little bit and then some energy pops out of invisibility into visibility. Then you travel a little bit further and more energy pops out of invisibility into visibility. And so if you wait a long time, it's more or less just a normal jet. But at the beginning, it was totally invisible and it emerges the longer you wait. So that was our proposal, and we were really excited about this. And it's a way to look for dark matter that's totally different than ways to look for dark matter that other people have thought of. And so I went and pitched this to all the experimentalists, anyone who would listen, basically. And some of them found this pitch convincing. So there's at least two groups who are working on this. There's one group at one of the experiments at the LHC called the Compact Muon Solenoid that published a paper. They spent a bunch of time and they looked at their data and they looked to see if they could find these emerging jets in their data. And they did not find them. So probably I'd be a lot more famous if they did find them, but they did not. But still, it was cool and they could have found them. But it was only a small fraction of the data, right? It was only the data taken in 2018, I think, in so one particular slice. And then there's the other big experiment at the LHC is called Atlas. And they're also trying to do this with a much bigger bunch of the data. And one particular thing that's cool about that is there are my colleagues here at Carleton, some of them work on Atlas, and they are some of the people who are working on this emerging jet search in Atlas. And so there are a bunch of students and professors and postdocs here at Carleton who are doing this work that is inspired by my earlier work. So it's pretty fun stuff.
So for an emerging jet, let's say we're looking at a sliver of data from the LHC, and let's imagine that it was an actual emerging jet, like you've predicted. What would that look like?
Yeah, good question. So these detectors so the LHC smashes protons, and then there's these machines that try to figure out what happened. So they look for the Higgs decays, or they look for emerging jets, or they look for every other thing. And they're sort of like an onion. They have different layers, and each layer has a different job. And so the innermost layer, its job is to look for charged particles moving through it. And so it basically draws a line of when a charged particle moves through the innermost layer. And so most of the time, the charged particles originate at the original proton-proton collision, and then they go out away from the proton-proton collision. And so what you would see if you had an emerging jet instead was lines of particles that don't start at the origin. They don't start where the collision started. They start sort of random places. And so one random place will have 3 lines coming out of it. Another random place kind of nearby, but not in the same spot, will have 5 lines coming out of it. Another one will have, and they'll all be sort of nearby, but not on top of each other. And there'll be these emerging lines coming out of them, all sort of in the same spot.
That's really interesting. So how, is there a way to, I don't know if this would be a question to ask you as a theorist or a question to ask an experimentalist, but how would you tell that these aren't just, I guess, like a neutral particle breaking into a bunch of charged particles or decaying into that?
That is absolutely the correct next question. Yes, because there are these things in the standard model that can do this, right? So there's this thing called the neutral kaon, which typically flies about 1 meter before it decays into charged pions. And so indeed, this can happen in the standard model, but it's very rare to have a bunch of these things sort of in the same spot or in the same region, right? So when you produce ordinary standard model jets, you don't typically produce all K-longs, right? You produce K-longs, but also protons and also neutrons and also things that are totally invisible and things that are totally visible. While this emerging jet thing, it doesn't, it's not like, it doesn't produce totally visible lines that start at the origin. And so you look, our proposal at least was to look for a jet with very few lines starting at the origin and a large number of lines starting far away. And then to also add up the energy of all the lines, because so I said it's an onion. The innermost bit of the onion draws lines. The next bit measures energy, and it measures energy of both charged and neutral things. Right. And so if you have a lot of, say, K-longs, you'll see a lot of energy in this measurement part of the onion with very few lines. And so if you can compare sort of how much energy you measured versus how many lines you saw, then you can get a sense of, is this a normal jet with just that happens to have a large number of neutral particles, boring standard model things, or is this one of these weird emerging jets? So that's sort of the simple version. That the actual experimental paper that did this did a fancy, complicated version of the same kind of thing. But yeah, that is the first question you have to answer. How can you tell the difference between boring background and the exciting physics you're looking for?
Well, actually, I'll make sure to link the paper that you just mentioned in the description of the episode. So for those interested, there will be a number of papers, some by Dr. Stolarski, another one, which is the experiment that he's referring to, and those will be in the description if you want to look at them in more detail. So you were mentioning, right, CMS and Atlas are currently looking for this in their old data. I guess this is kind of a stupid question, since it makes sense to look at the old. That's true. Like, do you think that you should be focusing more on like this old data that the accelerator has collected over all this time? Or would it be better to be focusing your efforts towards like looking at the upcoming new data from the high luminosity LHC?
Yeah, good question. I mean, on my side, in some senses, it doesn't matter. I think all of it is interesting, and we propose these techniques, and the techniques, hopefully, on my end, will work for the old data and for the new data. And then it's up to the experimentalists. Do they want to look at the old data? Do they want to concentrate on the new data? And so I think I said that they're mostly looking at the old data, but it's only, I mean, that's only because that's the data that exists. The work on the new data certainly has started. The new data hasn't been taken yet, but I know, for example, some of the graduate students and the Carleton team who are on Atlas who are doing this, they've sort of split their work, and some of them are looking at past data and some of them are looking at how can we improve with future data. So I think it's all interesting, and in some sense you want to combine all the data you have. But the future data, right, it's hypothetical data. It doesn't exist yet. You can't actually analyze it. So you can prepare to analyze it, but it is, in some sense, you obviously cannot make a discovery with data that doesn't exist. And you could with data that has been taken.
Right, that's very true. So is there any other sort of detectors that could be used to notice these emerging jets, or is is the LHC the only one that's really capable of doing that?
Oh yeah, great question. So, um, as far as I know, the LHC is the best at doing this of the detectors that exist. And it's sort of a simple reason, and it's basically the reason why it hasn't been discovered in the first place, right? The reason emerging jets haven't been discovered in the first place is in order to make them, you have to produce a very heavy particle, right? And so earlier accelerators, which had less energy than the LHC, did not have enough energy to produce this very heavy particle. The LHC is and will be for the foreseeable future the highest energy experiment in the world. And so it is the best game in town for this kind of physics. But it's not, there are other kinds of physics models, and some of them are sort of similar to emerging jets in the sense that they have this like signature of some invisible thing turning visible, but they're not produced via heavy particles. And so then there are other experiments that are probably much better. And so the jargon that the community likes to use is the energy frontier versus the intensity frontier. So the LHC is leading the energy frontier. It has the highest energy, but the intensity frontier means you just make a lot of collisions at very high frequency, and they don't necessarily have to be at such high energy. And so there are many experiments around the world that are sort of looking in that direction, that can discover things. But sort of a related question to yours is, well, the LHC is not just Atlas and CMS. There are other detectors at the LHC, which are not as big and not as sort of encompassing as Atlas and CMS, but they potentially could have some reach just to discover emerging jets. So one is called LHCb. And it's, so while Atlas and CMS are like a big cylinder, LHCb is more like a cone. And so it only takes a picture of particles that come out in a certain direction off of these collisions, not in any direction. But the name is because it's trying to do, or it was built to do physics of the bottom quark, the B quarks. And B quarks, they also live a long time before decaying, not quite as long as the emerging jets, but they fly a few micrometers, something like that. And so LHCb is designed to detect these few micrometers displacements and then do really cool studies of bottom quarks and things made out of bottom quarks. But because it's so good at measuring things that fly a little bit and then decay, it can actually be very sensitive to emerging jets. And then so LHCb is taking data, and we've tried to pitch emerging jets to them. We haven't seen any papers, but we think they are working on it. I'm not sure. But then there's these other proposed detectors. So, the LHC is going to be there. It's going to take 20 more years of data. So maybe there's other ways to exploit this data. And so one thing that I've worked on that was developed by David Curtin at University of Toronto and other people, but that I've since worked on, is this detector called Methuselah. And it's, so I think it's, you take an IKEA or a building the size of an IKEA and you put it above the LHC. So it's not connected to the LHC. The LHC is underground. This thing sits on top of the LHC. And then you put particle detectors on the floor and on the ceiling of this IKEA-sized building. And so when something gets produced at the LHC that's invisible, and instead of traveling like a few centimeters, if it travels a few hundred meters, it can then decay inside of this giant IKEA thing called Methuselah, and then it can be seen. So it's this proposal is sensitive to the same kind of physics, but where the lifetime parameter, the typical distance this thing flies, is quite a bit longer. And so that's currently being explored. They have some money to do R&D, and they have a proposed site. They're still fighting to get funding to build this giant thing called Methuselah, and that's the thing that I've worked on, exploring how well this thing could discover emerging jets as compared to Atlas or CMS, and that it can do pretty well for certain regions of how long these particles live. So that's another kind of thing that could be a discovery machine sometime in the future.
Awesome. So what is your overall hope for emerging jets? I'm assuming you're definitely hoping that they're found, because that would be amazing.
Yeah, exactly. So that would be amazing. I mean, but of course I can't control what nature does, what is the real theory of dark matter or whatever. So my overall hope is that people continue to work on it, right? Like that's the all I can really ask for. And so far, There's been a lot of success on that front. We've got this group at Carleton working on it, and this group in CMS, and hopefully Methuselah will get built, and people there can do dedicated searches. Of course, yeah, discovery would be amazing, and I'd spend the rest of my life working on only that. But even if it's not discovered, I just hope that the research continues on the experimental side.
That's awesome. So I guess the next question I can follow up here is what are you working on now, research wise? Because you have your work on the Higgs, your work on the emerging jets. I know you said you work on a few other things, including dark matter, which is kind of tied into the emerging jets. But yep. What's sort of the focus currently?
Like where are you going there's a few sort of different projects that I've been working on recently. So one thing is a different way to look at emerging jets, which is that quantum mechanics says that if you can produce a particle, you will produce it, even if it's not sort of energetically allowed. It's so the production of virtual particles that exist for a very short amount of time and then disappear again. And so potentially you can look for emerging jets through their virtual effects. So you never make an emerging jet, but you virtually make one of these dark quarks or dark gluons for a very split second, and then something else happens. And so this can lead to things that are, for example, very, very rare in the standard model to happen more often. So one example is there's the decay of a B quark, a B hadron. So a bottom quark turns into a bottom quark and a down quark. Together, they form a particle, which lives a little while, and then it decays to other stuff. And so this experiment called Bell 2 will make a lot of these B hadrons. And then we asked, well, if these virtual particles can cause a B to turn into an anti-B. So it's a bottom quark turns into a state with an anti-bottom quark. And this happens in the standard model, but it's very, very rare. And so if you can measure this happening slightly more frequently than in the standard model, it might be an effect of one of these dark pions virtually happening through something like this. So that's called flavor physics, is like detailed study of bottom quarks and charm quarks and other weird things that are not really related to things we see in our day-to-day lives. But Bell 2 is a big experiment doing this, and then the LHC is doing this also to some extent. I've also gotten interested in gravitational waves. So gravitational waves are ripples in space-time, which is a kind of crazy idea that the distance between two objects will shake, even if the objects are perfectly still. And so these were experimentally discovered in 2016 at this experiment called LIGO. And so I've been interested in what if there is a cosmic background of gravitational waves. So there's this cosmic background of photons called the cosmic microwave background that tells us, the study of the cosmic microwave background has told us a ton about the universe, and it's just photons everywhere. It's the sort of leftovers of the Big Bang that are all over the place. And because of the temperature of the universe, they are all microwave photons, more or less. And so the question is, could there be gravitational waves sort of everywhere, just streaming in at all times? And if so, could that tell us something about the early days of the universe? So that's something I've explored a little bit with some of my recent grad students. And then I'm doing further stuff a little bit further away from phenomenology, and just more, how does quantum physics work just at the more abstract scale, not necessarily connected to anything. And so we have this theory of the strong force, and the theory is built out of quarks, but we don't see quarks. And so that's weird, but it's been known for like 60 years that quarks confine. And this has been our working theory of the standard model, that you can't see quarks because the strong force is really strong, but there's never been a proof that this actually happens from first principles of quantum chromodynamics. And so I've been thinking about how can these confining theories, how can you study them in other ways using, fancy mathematical techniques. So I actually have a paper that will appear on the archive tonight when we're recording. So in November, but when this comes out, it will be on the archive and anyone can read it. So that's also something I've been thinking about.
That's really fascinating. You've got a wide range of things that you're working on, which is really cool.
Yeah, so that's that's my favorite thing about being a theorist, right? So if you're an experimentalist, you have to spend 10 years building this device, and if you don't spend all your time doing it, it will never work. But as a theorist, you can work on this and work on that and do them in parallel, and you can be a little bit ADHD and work on a whole bunch of different things because you lose interest in one and go around in circles. So I love it, and yes, it leads me to have a pretty broad research program.
Well, as we're kind of coming up to the end of the time, first of all, I'd like to say it's been a pleasure to have you on the show. It's been really cool to learn all about your research.
Yeah, thanks for the interview. You've asked great questions, and I hope your listeners enjoy this episode.
Yeah, but first of all, the final question, as I ask everyone. So what do you think has been the most impactful experience in your career in physics? You can pick more than one if you'd like. I've had people who have said, "Oh, I've got 3 of them." But most impactful experience on you for yourself.
Yeah, you did tell me you were going to ask me this one, and I thought about it for a long time. It's a tough one. But I think it's working with students and graduate students in particular, like teaching them to do research and then, going off and flying on their own in the research world. So it is very exciting to suggest something to a student and then they go off and figure it out. And then they figure out a whole bunch more things that I had never even considered. And then they're doing their own research. So I would say working with students who are doing their own research has been extremely impactful for me and hopefully for them as well, that they've gotten to learn some cool things and I've taught them things.
That's awesome. Well, again, thank you once again, Dr. Stolarski, for coming on the show. It's been a pleasure to have you.
Yeah, thank you so much.
Thank you for listening to this episode of The Quantum Mic. A big thank you to Dr. Daniel Stolarski for coming on the show this week. Join us next time for another episode of Relative Grace, where we will be talking about Gerhard Hertzberg. You can follow The Quantum Mic on Twitter at quantum_mic to stay up to date with the show. Let us know how we did by leaving a review and subscribing to the show. If you'd like to come on the show and talk about your amazing research, you can email us at thequantummic@gmail.com. This episode of The Quantum Mic was hosted and produced and edited by Owen Dara. The Quantum Mic podcast was created by Owen Dara, and the music used in this episode is by Kevin MacLeod. Thank you for listening, and we'll hear you next time on The Quantum Mic.